Einstein's theory of special relativity starts with two basic postulates, and what this means is these are the initial conditions for our theory. So these are the things that we're going to assume is true, and then we're going to work out the consequences of what if they are true. So this is a little bit like when you saw the kinematic equations at the very beginning of your first semester physics course. We start from the assumption the acceleration is constant and we only move in one dimension, and we get these equations. The equations don't prove acceleration is constant or that you're only moving in one dimension. And by the same token, we're not going to prove the two postulates of special relativity. We're going to assume them and see what they predict. Now, after having said that, it turns out that uh, special relativity is probably one of the most accurately confirmed scientific theories ever. There are no disagreements with it that anyone's ever been able to find. So we'll look at these two postulates and see how hard they are to believe. First one is pretty simple, and it's something that all the way back to Galileo people would have been able to believe, and it just says the laws of physics are the same for all inertial observers, and what inertial means is not accelerating. So if you look at all the labs you did in first semester physics, rather than being in the physics lab, what if you had been in the back of a cargo plane while it's flying at constant velocity? You wouldn't have been able to tell the difference. All your results would have been the same. There's no real physical difference between moving and being at rest. And that's one of the key features of relativity. There is no at rest. We always talk about our motion relative to the earth, but that's just because that's where we live. There's nothing inherently special about it. And if you're in the plane, what's really more important to you is the speed relative to the air, because that tells you whether you're going to keep flying or crash. The plane is just as much of an inertial system as our lab is, again, as long as no acceleration is happening. Now, the second postulate is crazy, although it may not seem that unreasonable at first. All it says is the speed of light in a vacuum is the same for all inertial observers. That seems okay, but here's the consequence. Last semester, if you imagine you're on a railroad flat car and the train's moving at 20 meters per second, and you throw a baseball, you can throw it 15 meters per second. If you throw it towards the front of the train, somebody standing on the ground as the train goes by would say the baseball's moving 35 meters per second. They would add the two velocities. If you threw backwards, they would do 20 minus 15 and say the ball was moving at 5 meters per second. This is just vector addition. You did this a million times last semester. The weird thing is, now let's say you have a flashlight instead of a baseball. We let the train still go 20 meters per second. You shine your flashlight towards the front of the train. You will say light is moving at this speed we've seen before, 299,792,458 meters per second. You would say that's the speed of light, assuming we're in a vacuum. Someone on the ground watching the train go by, Newton would expect them to get a value of 20 meters per second above the speed of light when they measure the speed of light, just like they got the value for the speed of your baseball as 20 meters per second above what you got. However, when they measure it, they get exactly the same thing you got, like the train wasn't even moving. So Newton and Einstein don't agree here on this, and they can't both be right. But what we do know, Newton can't be completely wrong. Newton's physics can't be complete garbage. Or number one, we wouldn't have spent the last semester and the one before it learning it. But number two, Newton was no fool. He would have figured it out, or somebody before Einstein would have figured out this doesn't add up. So the change is going to be very, very small. And we'll actually go over that math in the next few lectures. And what we're going to see is, instead of the baseball moving 35 meters per second, if we do this with better accuracy with the Einstein equations, what we'll get is this velocity, 34, and this long train of nines meters per second. So it's off by about 1/10 trillionth of a meter per second, and there's no way we'd ever measure that for a baseball. So it's no great surprise that Newton didn't see this. He didn't see that velocities don't add exactly like we've been treating them. There are more significant consequences of this. One of them is the relativity of simultaneity. So, as an example, there's a picture here from your book. We've got someone riding along in the train car, observer A, and someone watching. And here they're saying the picture we really want is a light over this observer A's head. Observer A would say light hits the front and back of the train at the same time. The light's in the middle. That's one way we would define the middle. So she would say light hitting the front and light hitting the back are simultaneous events. Someone watching the train go by would say, wait a minute, the light from the train's going to the right. Light leaving the middle of the train and headed to the right has to chase the train, has to chase that wall. But light going back this way is going to run into the wall, the back of the room that's coming towards it. So someone on the ground would say, no, light hit the back wall first and then the front wall. So the people on the train will not agree with the people watching the train go by about what things are simultaneous. So what things happen at the same time. Now we can put in some extremely high speeds and see how far apart their agreement would be. It's pretty dramatic. If the person on the ground here measures the train's velocity to be 0.9 c, then he sees the back of the train car headed for the light pulse, and the effective velocity, the rate that they close the distance between them, would be 1.9 c. He would also see that the light pulse is chasing the front of the car and gaining on it at a rate of 0.1 c. Now, even though when we say this effective velocity of 1.9 c, keep in mind nothing is traveling faster than the speed of light. Similar idea, what if we had two planes in a head-on collision where each is moving at 500 miles per hour relative to the ground? The effective crash speed would be 1,000 miles per hour. That's faster than the speed of sound, but nobody expects a sonic boom to come out of this because nobody's really moving faster than the speed of sound. So one of the things we need to take into account is the idea about an inertial frame and the difference between seeing and observing. And sometimes I might be sloppy with my terminology, but what we're really talking about in all these cases is what did they observe? So why is that different? What is an observer? Why do we need to worry about this? If you've ever seen a pile driver, something that drives big telephone pole things into the ground, you can hear that from a long way away, and you might also be able to see it depending on the surroundings. And what you'll notice if you're far away is the sound and the picture don't match up. You see the big hammer hit the telephone pole, and then a fraction of a second later you hear it. You can see this in a less dramatic way if you have somebody maybe at the end of a street bouncing a basketball. You watch the ball and you notice that the sound doesn't quite match when the ball's hitting, and that's because it takes sound a significant time to travel up to reach you. It travels at about 1,000 feet a second. Little kids know this. As soon as there's a lightning flash, you have them start counting seconds, and when they hear the thunder, they'll be able to figure out how far away the flash was, since the sound is traveling at 1,000 feet per second. The reason we never worry about this with light is, number one, there's nothing faster to tell us to start counting before we see the flash for lightning. But number two, light is ridiculously fast on our time scale. It's about 1 million times faster than the speed of sound, which is already pretty fast for us. So we don't want to have to worry about, when we say you'll see this, that, or the other thing, we don't want to have to worry about, oh, well, you'll see it, but it will take 500 nanoseconds for the light to reach you. So the way we fix this is we imagine you have an infinite number of friends and clocks and meter sticks. So we build this lattice, this grid work, and we imagine we have an observer at every point and a clock that's synchronized and a meter stick. And they're all traveling with you. Whatever you're doing, they're with you. When we want to find out what happens someplace, rather than worrying about light travel time, one of your friends will be right there at that location, so we can make the light travel time essentially negligible. We've got somebody everywhere keeping track of things. The only reason we do this is to keep it from being an even bigger mental load than it already is. Now, what is an event? Well, if you make an appointment with someone, you're actually scheduling an event. You give them 3 spatial coordinates, latitude, longitude, altitude if you've got a helicopter, and the time to be there. So these 4 numbers give us a single point in space-time, and that's what an event is. It's a single point and time. So let's say you're at the origin of your reference frame, so all your x, y, and z values are 0, and something happens 30,000 kilometers away from you on the x-axis at a time of t equals 2.55 seconds. It'll take 0.1 seconds for this explosion or whatever, the information about this, to reach you. So rather than delay everything by 1/10 of a second, what we do is we say, well, I've got a friend there. So they saw it happen instantly. So let's look at the first really weird thing. So far, this simultaneity thing, we don't agree on it, but you may not be very comfortable with what it even is yet. You're still just thinking about that. But what we're going to look at next is a really weird thing that will probably bother you.